We are nearing the end of this section. The next result is this theorem 6.8. So here we have two number theoretic functions, capital F and small f, and they are related by this equation. For any positive integer n, capital F of n equals the sum of the small f values of all the positive divisors d of n. You already know how these sums go. Now we have already seen in a previous result that in an exact same situation, if small f is multiplicative, then capital F is also multiplicative. But here the converse is true. If capital F is multiplicative, then small f is also multiplicative. And that is because we are able to reverse the roles of capital F and small f using our Mobius inversion formula. So I urge you to go through the proof. It's not very difficult. So you can go through the proof, and there are a few other things also here. So let's see what comes after this. So next we are going to consider the sum of all the mu values of the integers, positive integers less than or equal to some given positive integer n. So for any positive integer n, we are defining this function capital M of n, which equals the sum of the mu values of all positive integers less than or equal to n. Note that the type of sums we have considered so far, they are not like this. They run over all positive divisors of n. This is, however, different. Here we are considering all values of k from 1 through n. Then m of n is the difference between the number of square-free positive integers less than or equal to n with an even number of prime factors and those with an odd number of prime factors. Let's see this thing in an example and try to understand what this means. So as an example, we take the case where n is 9. So m of 9 by definition is this sum of all the mu values of positive integers less than or equal to 9. Now let's go back to the definition of mu and calculate all these mu values. First we have mu of 1, which by definition is 1. What about mu of 2? 2 is a square-free integer. 2 is not divisible by the square of any prime. And then you look at the prime factorization of 2, which is 2 itself. And how many primes are involved here in the prime factorization? 1. So minus 1 to the power 1. So that is why minus 1. And actually because of that, for any prime p, its mu value is going to be minus 1. Similarly here also 3 is prime, so mu of 3 is minus 1. 4 is not a square-free integer. It's divisible by the square of the prime 2. In fact, it is equal to 2 square. So this mu value by definition is 0. 5 is again prime, so minus 1. 6 is square-free, and in its factorization we have two distinct primes, 2 and 3. So minus 1 square. This exponent is the number of primes in the prime factorization of a square-free integer. 7 is again prime, so minus 1. 8 is not square-free, it's divisible by 2 square. 9 is not square-free, it's divisible by 3 square. So both these mu values are going to be 0. Okay. So those integers which are not square-free, they are ultimately contributing 0 to this sum. That means essentially they are not contributing anything. What about the remaining integers which are square-free? In their factorizations, for some of them, the number of primes involved is even, and in some of them the number of primes involved is odd. Which are the ones that have odd number of primes in their prime factorization? In this case, those are primes themselves, 2, 3, 5 and 7, and the contributions that they make in this sum are minus ones. Each one of them is minus 1. So you get 1, 2, 3, 4, 4 minus ones. So that's how you get minus 4. There are also two square-free integers here, and in their prime factorizations, the number of primes is even. Now it may be a little confusing if you think of 1 as well, 1 is square free by definition because it's not divisible by the square of any prime. In fact, it is not divisible by any prime itself. But the source of confusion may be this. You may have to think of a factorization of 1, which may not really make sense, but you may think of it like this. Because there is no prime, so that you can write 1 as a product of some primes. So the number of primes involved in the factorization of 1 is 0. In that sense, the number of primes involved in the factorization of this integer 1 is even, because 0 is even. So that way you may class this 1 with 6. Because in the prime factorization of 6, the number of primes involved is 2. That number 2 is also even. Ultimately, what matters is that these are the types of numbers which contribute 1 in this sum, not minus 1. The ones are coming slightly differently, but you may think of this one as minus 1 to the power 0. That is also 1. So for these two, we are getting 2. Now you see what is written here. M of n is the difference between the number of square free positive integers k less than or equal to n. Those numbers that are not square free, they have no contribution, so they have nothing to do with this sum. For the square free positive integers less than or equal to n, in this example less than or equal to 9, this m of 9 is the difference between the number of those square free positive integers with an even number of prime factors, like these two, and those with an odd number of prime factors, like these 4. And you can understand that this will happen in general also, for a general n. Now, what about all these things? Why are we suddenly considering m of n? Well, we are considering m of n here because it involves the mu function, which we discussed in this chapter, and mu, chapter means in this section, and mu was needed because we need it in Mobius inversion formula. Now, the final thing that author says about this m of n is a conjecture which was eventually proved to be wrong, Martin's conjecture. In 1897, Franz Martens made a conjecture, a guess about this function m of n. He published a paper in which there was a 50-page long table of values of m of n for these n values, in starting from 1 and ending at 10,000. And based on these values, he made this conjecture that the absolute value of m of n for any positive integer n greater than 1 is less than square root of n. You can test that conjecture with our n equal to 9. So m of 9 is minus 2, so its absolute value is 2, which is less than the square root of 9, that is 3. Is this conjecture true? No, it's actually not true. So this is what usually happens in number theory. I mean, at least it was like this long time ago. I don't know the current state of research. So someone would make a conjecture based on some hundreds or thousands of values, and then a proof would not be in sight. People will have no idea how to prove or refute the conjecture. So what then they will do? They will carry out a computer search. Such a computer search was carried out in 1963, and it verified the conjecture to be true for n up to 10 billion. That's a long range, very long range. So when you see that your guess is correct for 10 billion values of n, then it gives you hope that, yeah, maybe the conjecture is true. But it has happened again and again that in spite of having overwhelming evidence that something should be true, it ultimately turned out to be false. In 1984, these two mathematicians proved this conjecture false, and they did it with the help of some computer, and their proof was indirect. They showed that there must be some counterexample, but they were not able to provide an actual value of n for which this inequality will not be true. That is, for which the absolute value of m of n will be greater than or equal to square root of n, not less than. But now people know that there must be at least one counterexample for n less than or equal to this gigantic number. Okay, so the proof is there, the proof is an existence proof, or rather I should say disproof, that this conjecture is false, but no value of n is known for which it is really false. I mean, no concrete value of n is known, only its existence has been proven.